To the post-lunch session. We have how many? 4 25-minute talks here, and for each of them, the time for 25 minutes has to be judiciously divided at the speaker's behest between question and discussions, but the 25-minute deadline remains, and I will give appropriate indication by using a stick, which is not meant for intimidation. Because stick used for intimidation has a history in our community in this institute, but I'll tell you that story later. Okay. Stick used for intimidation. Okay, so our first speaker is Professor B. Ananthanarayan. He will tell us about hypergeometric function theory and Feynman integrals at the interface, some recent mathematica implications.
Thank you very much. I'm very pleased to be here to talk about the work done by a vast number of very brilliant students and some of our collaborators. And this has resulted in several codes that have appeared from here, which have now been published. So this is basically a commercial for these, and I encourage all of you to try to, download them and use them for your purposes. So both the topics in this title are well known to you. Hypergeometric function is ubiquitous in mathematical physics, and it has a long history, starting with, of course, the geometric series, which was generalized by Gauss in one variable, and subsequently it was extended to 2 variables by Appel, and then to n variables by Lauricella, and these happen to appear in Feynman integral calculations. So, but there's a rich theory that interlaces between the two, and there are many notions and ideas in this topic, and there are also implementations in Mathematica itself and in Maple, but some of them are erroneous because of various problems associated with multiply valued functions. So we have had a program where we have studied these things in great detail. So, so my talk will come in a few parts where I will describe specific packages that we have developed, and starting with a small introduction, and we can take questions as and when we go. So, so all of you are aware of this particular formula for a multi-loop, multi-scale integral, which looks like this. It's a product of several denominators of this kind, which contain combinations of momentum and also loop momenta, which appear over here, and one integral per loop over here, and various combinations of masses that appear over here. So this is a very generic Feynman diagram, and a lot of the things that we are talking about cannot really be done for more than 2 loops, and sometimes in special cases for 3 loops as far as analytic continuations are concerned. Here are very basic Feynman diagrams that we have over here, and they go under these names of a tadpole. There's something that looks like this. There's no external momentum flowing into this. This bubble is a very common diagram that you see, which has one external momentum. It's a one-loop diagram. And here's a one-loop triangle, which has basically these momenta flowing in. And here is a simple example of a 2-loop diagram, which is called a sunset, which is 2 loops over here. And in principle, this can also be having several mass scales, because there's nothing to say that in a physical problem, you'll have only one mass, common mass over here. You can have 3 different masses for internal lines. You can have different masses for external lines, etc., etc. So there are a large number of masses and momenta over here, and in general, you can't solve them for arbitrary configurations, but this can be done for specific configurations. And of course, many of these diagrams are also divergent, so in 4 dimensions. So we regularize these in dimensional regularization, and then treat it, and then we have to extract the various Laurent coefficients in the dimensional regularization parameter. So it also happens that you can change some of these parameters and then see how the Feynman diagram actually evolves as a function of one of the many parameters that defines the Feynman parameter. Here, for instance, is an example where we have a differential equation satisfied by a bubble diagram, which on the right-hand side contains other Feynman diagrams. So sometimes in life, we would like to solve these differential equations for these Feynman diagrams, especially if you know some of them already, which are simpler, then you may get an answer for a more complicated Feynman diagram by solving the differential equation. And of course, differential equations always require you to specify boundary conditions, without which you cannot solve them. So here is an example where you already see the appearance of a hypergeometric function. Here is a famous Gauss hypergeometric function denoted by 2f1 in these. So the first three objects given here, the parameters of the Gauss hypergeometric function, and this is evaluated with a variable x. So it's easy to understand or see why hypergeometric functions show up in Feynman integral calculus, because that's just the way they are. So I'll also, of course, give you some more examples of what kinds of hypergeometric functions show up. So here is a hypergeometric function with two variables. This is an example of what is known as an Appel function. So Appel, in the late 19th century, he found four generalizations of the Gauss hypergeometric function called f1, f2, f3, and f4. And one of them shows up in this particular computation, which is one of the Passerino-Weltman functions. So, you know, they show up all over the place depending on how many variables show up, where these variables x and y could be ratios of momenta and masses. And so those are the physical kinematical invariants that show up, which are expressed as these hypergeometric functions. So here is another example of a sunset. So what I mentioned so far are one loop. At two loop, we get the Lauricella C, what is called FC. So Lauricella there's a family of functions named after Lauricella, which has three variables in this case, and so on. So this is how these things are. So let me just say a few words about what these hypergeometric functions look like. Here's the Gauss 2f1, which has three parameters a, b, and c. And then what we see over here are these Pochhammer symbols, which is just a combination of gamma functions involving a and n. And then this is a sum, it's an infinite sum. Obviously it is a hypergeometric series, and it's an infinite series, and you have to sum over one of these indices here, which is given as n. So this is a very simple case. And of course, the Gauss f1 also, 2f1 also satisfies a differential equation. We also know that it has singular points at 1 and at infinity. So a very simple one. But the moment you go to two variables, it's already become far more complicated, because now you'll have two indices, m and n, and you can actually interlace these indices also. But you can't do it arbitrarily, and what Appel did was to study the various possibilities that will give you sensible hypergeometric functions generalized from Gauss. You'll have two variables, x and y, over here, and various Pochhammer symbols. See, the number of parameters is also growing. But the theory is now well understood, and it has been studied, and it has a rather limited range of validity, this particular defining series. Even the hypergeometric series, as it stands, is convergent only when x is less than 1. We all know, and we give this to school children, ask them to sum 1 plus x squared plus x cubed, and a bright kid will tell you it's 1 by 1 minus x, but this is true only when absolute value of x is less than 1. So similarly, we have constraints on what are the values that can be taken by these hypergeometric functions. So the Lauricella FC is also like that. And so it's not enough just to talk about hypergeometric series, but you also need to extend it beyond the fundamental region where it is defined. And you have to find analytic continuations. So part of our work has to do with actually defining it and then finding various analytic continuations essentially to cover this entire xy plane where x and y are the two variables. And there is quite a bit of science going into how to extend this and how to find all this. For instance, in a physical problem, your kinematic configuration may correspond to something like this red point over here. So the defining series, it doesn't converge, so you have to find an analytic continuation in order to get there. So this is the basis of the work that we have done, and these are the various Mathematica packages that we have constructed. So this is in a certain order. There's two. I don't have enough time to explain why this order. One of them is called Feyn GKZ. It combines Feynman diagrams and three Russian authors who describe these hypergeometric functions in terms of a generalization of a formula given by Euler, which is an integral representation. So this analyzes this particular system. This is another code in which we actually solved Mellin-Barnes representations, which appear in many branches of mathematical physics, not necessarily only in Feynman integrals, using a method known as conic hulls, which allows us to solve this problem completely. Now, this business of finding the analytic continuations is always complicated and difficult, and there was a method given by Olson about more than nearly 60 years ago, which was very painful to do by hand. So we have now coded this, and this is named after the author, and it's called Olson.wl, well, the author, whoever he was. Then we have other packages which evaluate the Appel F1, F2, and F3 over here. This one is already published. F1 and F3 are sitting in a different package due to Shovik and Tanay. And they have also extended it to evaluate various Lauricella functions over here. And Shovik actually has written packages where he does expansions of many of these functions which appear as multiple polylogarithms and so on in the dimensional regularization parameter. He has 2 papers over here like this. So a lot of this work started actually with this code which is called Aspire, which was developed by my former student Ratan, who's here for the first time after many years. So welcome back. So all this game started basically with this work. And here is another one where we studied various functional relations among Feynman integrals, which is also coded. And finally, there's one in which there is a 2-dimensional extension of Pade approximants, which again has not been coded by anybody, but this was done by Tanay and Shovik. Okay, so these algebraic relations arises from certain ideas that were first given by Tarasov, where he says that if you have denominators of this kind, you can, which appear in, say, a bubble diagram of this kind, and then you try to rewrite it in terms of other propagators and establish a functional relation arising from different combinations of such propagators. In other words, on the left-hand side, you have a given Feynman diagram. On the right-hand side, you have a sum of Feynman diagrams. And the hope is that on the right-hand side, you may find some simpler objects compared to what you have on the left-hand side. So this also is a fairly complicated problem how to do this. But we have done it, and we have also automated this in this program that is known as AlgRel, where we have found a way in which we can systematically and recursively solve for such things. So, among other things, of course, it gives you relations between various Feynman diagrams. Here is a Feynman diagram that you started out with. On the right-hand side, you have a Feynman diagram with a couple of massless propagators. So, you are relating massive and massless propagators also. So, this is a way in which I think in future people could use this as an input into computations that they are doing. And in addition to this, this also can give you relations among hypergeometric functions, because both on the left-hand side as well as on the right-hand side, you will get hypergeometric functions. Such relations are known as connection formula, which has been established for all sorts of hypergeometric functions. But this is an automatic way in which you can generate new connection formulas between this. So here is an example of such connection formula, not all of which have ever appeared in the literature, and this may also help others in future. So that is one of the things that we did over here. So the previous example that I gave you was where you have only 2 propagators. This you can do again and again and again. You can do it for 3 propagators, you can do it for 4 propagators, etc. So this thing, our code actually can do this with a set of inputs that you give. So you can download this and then install it, and then there's only one command in this paper which is called AlgRel, and then it has various user given inputs such as the number of propagators, the various parameters that define the propagators, and out comes an answer on the right hand side which tells you whatever is expected on the right hand side. So this is the summary of AlgRel. Then I want to move on to this this thing about evaluating or solving the GKZ system for Feynman integrals. As I mentioned, there's an Euler representation, an integral representation, which relates the 2f1 to an integral on the right hand side. So you may start to ask if you have an integral representation for a Feynman integral in a certain way, can it be mapped to a corresponding hypergeometric function? So this is what was studied by these authors, GKZ, Gelfand, and some others about 30 years ago. And they didn't do this in the context of Feynman integrals, but only from the viewpoint of the mathematics associated with the partial differential equations satisfied by these hypergeometric functions. I'd already mentioned that the Gauss 2f1 satisfies an ordinary differential equation. It has to, because it has only one variable. So all the other hypergeometric functions have to necessarily satisfy PDE's, partial differential equation, which in general are far more complicated than ODEs. But you can try to find solutions inspired by ODEs in order to solve PDEs also. And the coefficients that appear in such integral representations are not all free, but they get interrelated to one another because they have to satisfy more equations. So GKZ gave an algorithm for trying to take a particular A-type integral and then to find the corresponding hypergeometric series associated with that thing. So this algorithm was given, and recently some authors showed that there's a very specific way of rewriting Feynman integrals, which is called the Lie-Pomeranski representation, which allows you to map it to this GKZ system, and then what appears is an integral, is a matrix that is called A, and that's the reason why they are called A hypergeometric system, and it is associated with the various expressions that arise that describe this Feynman integral, the various powers associated with these monomials over here. So this A matrix contains all the information that you need in order to map it to the corresponding set of hypergeometric functions. So this algorithm was given, but again, there was no computer realization of this. And my brilliant students, only one who's left here now, Sudeepan, and some of his colleagues who have now left, they solved this system and wrote a beautiful code. And this is how it works. And it gives you, given a Feynman integral, you find the Lie-Pomeranski representation, then you feed it to the computer, and out comes the series solution associated with that. So this worked, yes, 10 minutes, Jesus, okay. Okay, so that was Find GKZ. So this was the second thing that I wanted to mention and talk about. I also want to say a few words about this Olson, which has to do with hypergeometric functions with more than one variable. So you saw in the very definition of these hypergeometric functions that there were two indices that we use which interlace the various Pochhammer symbols. But for functions of only one variable, there are all kinds of analytic continuations known. So you may want to group things in your two-index object and then do an analytic continuation of that, and then unwrap it and again re-express it in terms of the two-variable hypergeometric function, thereby finding analytic continuations. So that is the whole idea of what Olson did, which is a very beautiful idea, but it's very cumbersome to do by hand. So what was done by us was to take this algorithm that was given by Olson and to completely rewrite it on the computer using Mathematica, so that now the user can download it. He or she can feed in their hypergeometric function, give 2 or 3 examples, and then Olson will produce the analytic continuations that you may want to have. Okay, so what was done in the slide was to get an output from Find GKZ and then feed it into Olson and then re-express the answer in terms of well-known functions of two variables, which are cousins of the Apple function known as the Horn functions. One of them is called H3, another one is called G1, and so on. It's very beautiful, all this work. So it's almost like an art, I might say. So this is basically what I had to say about this GKZ system. So let me say a few words. I've already described this Olson a little bit. So one thing, of course, is to find the analytic continuation, but in all this game, it's not enough just to find the analytic continuation, but you also have to find the region of convergence of the analytic continuation. So that's the reason why this also contains a piece that is known as ROC2, standing for region of convergence in two variables. So this is a very beautiful package, and both of them have to be used together to find all these large regions where a given analytic continuation converges. So once again, these are rather straight, not so difficult to use. Anybody can download this and find various analytic continuations. Here, for instance, analytic continuation of 2f1. And we want to use all these options that are available and use various transformations associated with great guys like Euler. That's what E stands for, and P stands for Pfaff. So these are all the people in the 19th century and earlier who had studied many of these things to get various analytic continuations. So all the options and so on, everything is described very nicely in the documentation that we have given, and we encourage you to use it if you're going to do some of these calculations. So here's a demonstration of Olson where, this is what you have to do. So sorry that there's so little time to describe all this. So here is an example where you start out with this diamond over here, and then you use what was given in the previous slide, the various commands, and find this orange region where you have an explicit expression now for the analytic continuation and the region of convergence. Of course, this is still only a small part of this xy plane. Then you have to use yet another analytic continuations and go elsewhere. Basically, you can cover everything for the function f2 except the singular lines. By definition, singular lines are there where you cannot find anything that converges. So that's how it is, and we re-express all the answers in terms of the building blocks of hypergeometric functions. this is another important thing. This Apple F2 is another very ubiquitous function. It has also been studied, and we published a paper, myself with Shovik, Samuel Frio, Oleg Marichev, who's a very famous Russian mathematician, who I think Ukrainian, who now works for Mathematica Corporation. He has written several volume sets on these functions, and he's the one who actually constructs many of the functions for Mathematica itself. Except for the Apple F2, there were a lot of problems. So he joined us in this project of writing this. And we now have all kinds of analytic functions, continuations. But there's a slight problem associated with numerical evaluation of these things. And we solved that problem also for real values of x and y using specific prescriptions for evaluating the values of the functions on the branch cut. So we had to train Mathematica with a large bunch of if-then commands and so on, and make sure that the correct branch is picked, and therefore we get an unambiguous, thereby correct answer. Mathematica was giving a lot of wrong answers with its inbuilt function. Now they have a new version, I believe, but I don't know the current status of these things. So let me try to finish my talk now. I just wanted to say that there are many things which are unexplored. For instance, the use of dispersion relations for Feynman integrals have not been thoroughly worked out. There are numerical methods to do these things, but it would be very nice to push these things analytically. Then there are other mathematical properties associated with Feynman integrals, associated with names of mathematicians such as Hodge. Some people have done some work, but then after 1 or 2 years they give it up, and then they go back to numerical ways of evaluating this. There are also many methods from algebraic geometry, number theory, and so on, which all enter this because of the kinds of representations I had mentioned. Lee Pomeranski was one of them. Even in the Feynman representation, you get the equation of a curve, which could be an elliptic curve in some cases. It could be higher order Calabi-Yau varieties and all these things. And to analyze them and to get as many properties as possible analytically from this. So there are other things that we hear of these days: iterated Eisenstein integrals, iterated Chen integrals, theory of differential equations. Many of these things need to be worked out. Then there's another little direction which is called the theory of chords, which is associated with the mathematics of combinatorics associated with these very complicated Feynman diagrams. And these are all topics that are essentially in their infancy. So these are all topics in which people can work and have a very fruitful discussion. So I think I've used my time judiciously, at least in my opinion. I've lulled everybody into sleeping. Yeah.
Very judicious, Anand. Thanks for
Thank you.
finishing well in time. Now we have time for a couple of questions.
Yeah. Yes.
Amol.
So here we express the Feynman diagram
Yes.
and the solution of a differential equation of some.
Yes. Yeah.
So does this insight necessarily make calculation easier?
Yes.
Or is it
yes.
just happens?
No, it makes it easier. There are some packages which, do these things, and it's particularly useful if you introduce an epsilon expansion, where epsilon is the dimensional regularization parameter. And order by order, you can try to use this. There are some packages by various, essentially German groups, mainly Western European groups, which have developed many Mathematica packages to solve such differential equations.
So you perhaps partly answered my next question.
Yes.
Which is, for example, your diagrams on the right hand side.
Yes.
Had one loop diagram and
Yes.
one cadpole kind of diagram.
Yes, yes.
And so you have to do regularization for those diagrams.
Yes.
And
Yeah.
solving a differential equation with some part which needs to be regularized has to be done carefully.
Yes,
So
yes.
that technology exists.
For some diagrams, not everything is exhausted, but there are many specific cases for which these things are done. And they are all very useful and have been used. So Shovik's two epsilon expansion packages are extensions of other packages using more modern methods. Yeah. So did I answer your question?
Yes.
Yeah.
Okay. I think I saw one hand going up in this direction. Okay.
Isn't this the same as master integral method, at least the first part of what you mentioned?
Part of it. The thing is, let me also say that in general you can have a very large number of diagrams with all kinds of Lorentz indices and all kinds of combinations of propagators and so on. But in general, these can be reduced using all kinds of properties, integration by parts, routines, and so on, to a handful of basic integrals that you have to evaluate, which are called master integrals. Although there's no theorem which tells you that you have found the correct set of master integrals, there's no theorem which even tells you that what the number of master integrals is. There are again various codes, and most of them are correct most of the time, but occasionally they may give you an overcounting. So one has to, well, people like Ananthanarayan and others are here, Sudeep, and they're all experts. But once you find the set of master integrals, you'll have to be able to solve them. Yeah. So did I answer your question? Yeah.
One more.
Yes.
Please make it very short because we are
Just one sentence,
Time,
one
please.
question. So,
Master question. Yeah.
so with this method, can you go to higher loops efficiently?
There are bottlenecks. I think there is a stage. There are people who do 3 loops and so on, but they need all kinds of clusters. They need supercomputers to do all these things. There's a Laporta algorithm which is very popular. It's been used for a long time. So it's a whole science in itself. Yeah.
Thanks.
all right. With this, let's thank Anand very much for this very